Hello everyone. In this video I will be covering section 5.4. But before we go to section 5.4, let me refresh what we did in the last video or last section. Last time we talked about Taylor methods of order n. The method or the difference formula looked like this, where Tn was equals to all of this beautiful thing right here. Now remember one of the main advantages of this method, so one of the main advantages, and this is why we did it last time, is that they have a high order local truncation error. So this is the reason why these methods are good. However, these methods have a big disadvantage too, and the main disadvantage is the following. The method requires that you compute the derivatives at every point, and that can actually be very complicated or time consuming. So even though the methods have high order local truncation error, this is going to take, or it can take too long, or it can be complicated to solve. So that's why this is not the best or most efficient method. So therefore, in section 5.4, we're going to look to a new kind of method, or they're called Runge Kutta methods. And these methods are going to preserve the high order local truncation error, but the advantage is that you don't have to compute the derivatives at every point. So therefore, these ones do not require to compute and evaluate the derivatives of f of ty. The basis for this section, as it has been in the past, is going to be Taylor polynomials. More specifically, this is something that you may have not seen in the past. We're going to have Taylor polynomials in two variables. Theorem 5.13 describes exactly the expansion of a Taylor polynomial in two variables. It says the following. Suppose that f of ty has n plus 1 derivatives which are continuous in the following set. Then if this point also belongs to the set, then for all the ty belonging to the same set, there exists two variables, c and mu, such that the function can be written as a Taylor polynomial in two variables plus the remainder. So this is going to be the Taylor polynomial in two variables. Okay, and r of tn is the remainder, which is going to be used for the error. So in this case, it's just the remainder. Now, just to refresh your memory, we have done this multiple times in the class by now. But remember, you have a function and you want to write the Taylor polynomial. If this is created around, let's say, t0 in one dimension, this looks like this. T minus t0 plus f double prime t0 over 2, t minus t0 squared, and so forth. Okay. So this is the same idea, except this is in two variables. For example, this part is this. This part is going to be all of this now. So it's going to be the partial derivative instead of derivative, and of two variables instead of one. And then for the second derivative, just this, you're going to have all of this. So as you can see, it's a lot more messy, but it's the same idea. And then finally, this is going to be the remainder, which is pretty messy too. Okay, so let's do an example or illustration to see how you do Taylor series into two variables. Let's say you have the following function, f of ty is equals to e to the t ln y, and this will be t0, and this will be y0. Okay. Now, to make the notation a little bit easier to understand, remember that the partial derivative of f with respect to t can also be written as f of t. So this will make it easier to write these long formulas. The same way the partial derivative of f with respect to y is just f of y or f of y. And you have the partial derivative of f with respect to t, then with respect to y, this is the same thing as f of t y. Okay, this is usually the notation that is used in calculus, and for our purposes, this is actually more friendly than this one. All right, so if we go with our notation, then the derivative of f with respect to t, in our case, it will be e to the t ln y, and then from here, f of t evaluated at 0, 1 is e to the 0 ln 1, which is equals to 0. Okay. Then f with respect to y, it will be e to the t. It's a constant now. The derivative of ln y is 1 over y. So that means f of y of 0, 1, it will be e to the 0, 1 over 1, which is equals to 1. Then if we do the derivative with respect to t and then with respect to y, this will give you e to the t ln y, which again, if you evaluate f of ty, okay, let me fix this part, f of ty evaluated at the point 0, 1 is again just equals to 1. Now f of t with respect to t, or tt or double t, this will be e to the t ln y. So if you evaluate this at the point 0, 1, is again equals to 0. If we do f of y, this will be e to the t, and then it will be minus 1 over y squared, which means the f of y evaluated at the point 0, 1 equals to minus e to the t times 1 over 1, so this is just negative 1. This should be e to the 0, so that's negative 1. Hence, the Taylor polynomial in two variables of t, y is going to be f of 0, 1 plus t minus 0, the partial derivative of f with respect to t at 0, 1 plus y minus y0, the partial of y, and then plus 1/2 will be t minus 0 squared, second derivative evaluated at 0, 1, plus 2 t minus 0 y minus 1 f of ty evaluated at 0, 1, plus y minus 1 square times f of y evaluated at 0, 1. Notice that since I'm factoring the 1/2, that's why I need a 2 in here, because there was no 2 here, so 2 cancel each other out. Now, if we simplify everything, remember that f of 0, 1 is equals to 0, so this is gone. The partial derivative evaluated at 0, 1 of t is also 0, so is the second derivative. This one is equals to 1. This one is also equals to 1. And this one is equals to negative 1. So if we simplify everything, this implies that the second order polynomial in two variables will equals to y minus 1 times 1 plus 1/2 times 2t y minus 1 times 1 minus, it should be minus y minus 1 square, and that's it. In the next topic, which is Runge Kutta methods of order 2, we're going to use a process very, very similar to this. Actually, it's the exact same process to derive the method. So the idea is it's pretty simple. The idea is the following. You want to find three parameters, A1, alpha 1, and beta 1, so that when you do the Taylor expansion in two variables of this function, is equivalent or approximately equals to the Taylor method of order 2 that we did in the last section. Remember that this was equals to f of t y plus h over 2 f prime of ty. However, here you have to keep in mind that we're dealing now with partial derivatives. Remember, so recall, and this is from calculus 1, the f prime of ty, remember that's what we're trying to avoid computing. By definition, this is the derivative of f with respect to t of ty, right? This is still a regular derivative. By the chain rule, this is equals to the partial derivative with respect to t evaluated at ty plus the partial derivative with respect to y of ty times y prime of t. If you remember this from calculus 1, yes, actually calculus 1 or calculus 2, and even in calculus 3, this is the chain rule. Okay, so this is the chain rule from calculus. But remember that this part is the same thing as just f of ty. That's the definition. So therefore, this is equals to f of ty plus h over 2 f of ty plus f of ty times the partial with respect to y of ty. What about this side? Remember, this is a1 f of t plus alpha 1 y plus beta 1. So what happens to this side is you expand it in the Taylor polynomial in two variables. Well, if we follow the same formula that we did in the last illustration, this should equals to a1 f of ty plus a1 alpha 1 partial of f with respect to t plus a1 beta 1 partial of y with respect to partial of f, sorry, with respect to y. And here we're only doing the expansion up to this point, so therefore the last term has to be the remainder, which in this case it should be a1 r1 of t plus alpha 1 y plus beta 1. Okay, where, okay, so where r1 of t plus alpha 1 y plus beta 1 should equals to alpha 1 squared over 2. I'm just following the Taylor expansion, and you should verify this, plus alpha 1 beta 1, the partial with respect to t, then with respect to y, can see mu, plus beta 1 squared over 2 f of y evaluated at c mu. Okay, you should check that this is what you get from the Taylor formula that I did in the previous illustration. Is exactly the same thing. Just had to follow the formula and watch out for the algebra. So remember that this psi, all of this in blue, has to equals to all of this in red. So therefore, if you set it equal to each other and compare the coefficients, so you can see that, well, this has to equals to this part. So therefore, from there, that clearly means that if you look to f of ty only, that implies that a1 has to equals to 1. If we do the same thing with the partial derivative with respect to t, which you have it in here, then you can say from this derivative, the a1, which you know is equals to 1, alpha 1 has to equals to h over 2, which means that alpha 1 has to be h over 2. If we do the same thing for the partial derivative with respect to y, which is this part right here, this and this, including the h over 2, then that means the a1 beta 1 has to equals to h over 2 f of t y, or the beta 1 is just equals to h over 2 f of ty, because a1 is equals to 1. So that implies the t2 evaluated at ty is equals to f of t plus h over 2 y plus h over 2 f of ty minus r1 of t plus h over 2 y plus h over 2 f of ty. Okay, remember that this was alpha and this was beta. Okay, where if you plug those values in here, then we get the r1 of t plus h over 2 y plus h over 2 f of ty gives you h squared over a, and you should double check this. F, the second derivative with respect to t, evaluated at c mu plus h squared over 4 f of ty. The derivative with respect to t first, and then with respect to y, evaluated at c mu, and then plus h squared over a times the function square times the second derivative with respect to y, or the second partial with respect to y, evaluated at c and mu. Now remember that all the second derivatives are bounded because they are continuous. So therefore this implies that this is a round order of h squared, which is the same, so this is the same as the Taylor method of order 2 that we did in the last section. Now let's consider the following difference equation method of this form, okay, which is actually called the midpoint method. Now notice how this is very similar. Actually, this is identical to the Taylor method of order 2. It will replace this part instead of t of 2. So pretty much the midpoint method is a specific Runge Kutta method where t of 2 is replaced by this. Notice how only 3 parameters were needed to approximate t of 2. This is what I mean. So the approximation we used was this: t plus alpha 1, y plus beta 1. So pretty much you have 3 different parameters, and that's all you needed to approximate t of 2. And remember, the order of convergence for this one was O of h squared. Well, what about if you wanted to approximate something higher, like O of h cubed? So in that case, then if you wanted to do something similar for t of 3, remember t of 3 was equals to f of t y plus h over 2 f prime of ty plus h squared over 6 f double prime of ty. So therefore, probably the most appropriate way to approximate this, it will be something that has 4 parameters, and it will look like this: t plus alpha 2, y plus delta 2, f of ty. So this will require 4 parameters, but even with these 4 parameters, you don't have enough, there is not enough flexibility to approximate or to match the term. It's going to be like this: h squared over 6, and then the partial respect to y of ty squared. So when you do the Taylor expansion into variables, you will see that you won't be able to match this term. You should try that by yourselves and convince yourselves that you won't be able to do that. Hence, the best you can do with something that looks like this, and these four parameters is something of order 2. So therefore this implies the best you can do is OH squared. However, that gives us a kind of flexibility, which means you can come out with several methods that have order of H squared. I mean, there are several methods you can derive, so you will have several methods that will have O of H squared. One such method is called modify Euler's method. So modify Euler method implies that A1 is equals to A2 is equals to 1/2, and then alpha 2 will be equals to delta 2, and it will equals to H. And it will give you the following difference equation. This one right here. So this is the usual starting conditions. And the next value for W is going to be given by this difference equation right here. And this will be true for I equals to 0, 1, 2, all the way to N. Notice that here we have f of ti plus 1. Remember that ti plus 1 is the same thing as ti plus h. And why is that important? Because remember here this is supposed to be t plus alpha 2, where alpha 2 was equals to h. So therefore, if you pick these values in here, it will give you this method. Notice that the method requires to evaluate the function 3 times here, then in here, and then here again. All right, now let's compare the modify Euler's method with the midpoint, which remember is a Runge Kutta of order 2, and see what we get. This is the same example that we've been using all along in chapter 5. For the modify, remember that here we have h is equals to 0.2 and ti is 0.2i. So therefore, for modify, we're going to have wi plus 1 is equals to wi plus h, which is 0.2, f of ti, which is 0.2i, plus h over 2, which is 0.1, and then this should be wi plus h over 2, which again is 0.1, times f of ti, which is 0.2i, wi, which is equals to wi plus 0.2 times, here remember this is the first variable, you could say this is x, this is y, so therefore, or you could say this is t, this is y, so then this will be wi plus 0.1 f of 0.2i wi, and then minus, okay, all of this, minus t squared, which will be 0.2i plus 0.1 square, and then plus 1. So once you do all the beautiful algebra and simplify, you will get something like this: 1.22 wi minus 0.008ai squared is 0.008i plus 0.21a And remember here, I goes from 0 to n minus 1, which is in this case is 9. Also, don't forget this part right here. This is f of point 2i wi. So this will give you wi minus 0.2i squared plus 1. Okay, so once you simplify everything, you'll get this. If you do the same thing for the modify Euler's method, you will get the following: wi plus 1 is equals to 1.22 wi minus 0.0088i squared minus 0.008i plus 0.216. And again, I is equals to 0, 1, all the way to 9. The following table shows the computations of the two methods, so you can compare both of them. This table compares the results of the calculations of the two methods. And as you can see, for this particular example, the midpoint method is more accurate. It's closer to the answer for much of the steps than the modify Euler's method. So for this particular example, the midpoint method is actually much better. All right, now let's look to a higher order Runge Kutta methods. All the methods that we've seen so far are of order 2 or OH square. So how do we get higher order? So there is a way to get OHQ for the Taylor method of order 3. All right, so how do we do that? Well, you use this by using an expression of the following form. Okay. F of t plus alpha 1, and then the second argument is going to be y delta 1 f of t plus alpha 2 y plus delta 2 f of ty. This is f. This involves the finding 4 parameters, 1, 2, 3, 4. However, finding those parameters is very tricky. The algebra is very, very messy. But if you are bored and you have nothing to do, you should try this by yourselves. The most common method of OH3 is called Hume's method. Again, the algebra required to get this is very, very messy, but if you are up to the challenge and you are pretty bored and you have nothing else to do for a few hours, then you should give it a try. So again, Hume's method is the most, so this is the most popular or most common method of order of HQ. And this was actually invented in 1900, so 120 years ago. Okay. So if we apply this method to the same equation we've been using all along, to y prime is equals to y minus t squared plus 1 between 0 and 2 with the initial condition equals to 0.5 and equals to 10 and h is equals to 0.2 and ti is equals to 0.2i, then the results are in the following table. And as you can see, this method is way more accurate than the previous two, which should be no surprise because this is OH3, while the previous ones were OH2. As you can see, the error is very, very small compared to the previous two methods. Now, even though this is way more accurate than the last two methods, Runge Kutta methods of order 3 are very rarely used. The most common ones are order 4, which is the next one and the last one we're going to see in this section. The last method we're going to focus on is the Runge Kutta method of order 4. And as the name suggests, this one is OH to the 4. And in theory, this is going to be the best method we're going to use, and you'll see why in a little bit. The method is the following. So this is a difference equation, this one and this one. As you can see, this one requires 4 evaluations for each step. While you remember the very first one we did, Euler's method only requires one evaluation per step. However, this one gives you OH to the 4, which is far better than the previous 3 methods we did, but it is more time consuming. As you can see, in all the Runge Kutta methods, the most effort is obviously used to compute the value of f. Okay, so that's the basis of all the Runge Kutta methods, which raises a very obvious question. Can we have a higher than h to the 4? And if we do, is it desirable to do it? And the answer is actually no. For example, let's say that we have a small table, and here you have the evaluations per step, and then this will be the best possible local truncation error. Okay. So if the evaluation per step is 2, therefore the best possible truncation error will be h squared. If this is 3, this should be OHQ. And if this is 4, this is why we're going to stop here, this should be OH to the 4. However, if it is between 5 and 7, so this will be HN minus 1. So as you can see, it's not going to be matching the values in here. And if it is between A and 9, then it will be N minus 2 and so forth. So you can see after this point is not good. So that's why this is the best we can do. This table has the values. You can see that the error is very small. Now, like we say already, the Runge Kutta of order 4, it requires 4 steps, and the modified Euler's method requires 2 steps, and Euler method requires only 1 step. So therefore, if we're gonna say that the Runge Kutta of order 4 is better, for example, than this one, then this method should be more accurate with 1/4 the step size as Euler, because this one requires 4 times the work. As you can see, this one is 1/4 of this one, but yeah, this is still more precise than this one compared to the exact solution. This one requires half the work of this one. So it is supposed to be better than if using half of the step size of this one, it should give you more exact approximations, which is the case too. So that's why we say that this is the best of the methods we have so far.